Okay, good morning. Can any of you hear my voice?
Good morning, Anj.
Okay, thanks. Okay, let's start. We are in the chapter 4, right? The harmonic force vibrations, a case where the single degree of freedom system subjected to the external force, and the type of the kind of the external force is a harmonic force. And we found the solutions of this kind of force, the force vibrations in the general terms is called the total solution, as in equation number 32. In number 32, the total solutions consist of the two parts. The first part is a homogeneous part of the solutions that taking care about the initial conditions of the system, and is contained in the term the two constant, which are the xh and the phi h, the amplitude of the homogeneous solution xh and the phase difference of the homogeneous solution phi h. And the second part is called a particular solution. This particular part is the part that make the equilibrium of the force left and right side of the equations of motion to be equal, as in equation number 27. If you introduce the particular part of the solution back into 27, you will find to make the left and the right of the force equilibrium to be equal. That's why they call the particular solution to these equations. And for sure, if you introduce the total solution, I mean the combination of the two sets of the solution, the two parts of them, homogeneous as well as a particular non-homogeneous and sometimes called particular part. If you introduce 32 back into 27, you will see the same thing. Okay, where the left and the right hand side of the force equations will be equal. Since the first term, the homogeneous term, there's no effect on the solution. I'm sorry, here, right? 32. There's no effect because when you introduce the first part of 32 homogeneous solution, if we make something like this, right? If I consider only the first homogeneous part of the solution, you will find something like this. Homogeneous, only the homogeneous part will be introduced. Plus homogeneous of the homogeneous equal to 0. This is the fact that a homogeneous solution is derived from these homogeneous equations. If you make the things to be 0, the summation of the inertia term, damping terms, and the stiffness term be zero. That's why we include the homogeneous solution into 32 as the total solution to taking care of the arbitrary, initial conditions that you need to arbitrary parameters or constant. Okay, so before we go into more detail, I think there's some questions from your friends, your colleague on my example. Milin asked me about this one, that the number or the example that I provide, it shows something in errors. And I have checked somehow on this one, maybe I found something like this. I think the XP as in equation number A, right? The XP and phi P is good. This one and this one I have checked and I found is quite accurate. It's good. However, I found myself is the power -2, maybe could be power -3. Instead of -2, maybe you better check this one, whether it's power -3 or not. And I found something, this one here, the sign convention. Plus sign here, it could be minus sign. Okay. And if the power change to -3 and the sign change from plus to minus sign there, it could affect on the solution of the XH and phi H. So maybe you need to introduce the initial conditions again. When time equal to 0, maybe x0 be 0, x dot 0 be 0, and obtain the XH and phi H again. After you collect the sign convention and the power of -3, maybe. Let's check it yourself. I think it's not so difficult to do so. And for sure, if you ask me how to confirm that your solution and your initial everything, the total response is good or bad, is correct or not, it's pretty easy. Before that, I found something here also, like this term. It should be XP, right? And this term should be phi P as well. The sign convention there. Okay, I'm sorry for the errors that we found in the example, but I think the idea or the concept is quite straightforward, that you can check and prove by yourself. And the bottom line is, after you obtain everything, I think this is a total solution or the total response once you introduce everything into the equations and solve for the XP, phi P, XH, and phi H. I will ask you to check something like this. The first thing, you have to check 3 checks together. One thing, the first thing is to check the equilibriums. If you want me to check whether my solution is good or bad, correct or not correct, the idea is very simple. You have to check equilibrium, right? You have to check the first is about the equilibrium. How to check this? You have to introduce the solution as in this equation back into the equation of motion. Where is the equation of motion? I can write down for you here, maybe. It's better to provide you the equilibrium have to certify this one. Oh, I'm sorry. X double dot equal to, I think we already introduced F0. This is F0 and psi big omega T. That's it. This is a equilibrium that your total solution here in the red color have to satisfy. If your solution you obtain cannot satisfy this equilibrium, it means your solution is not the solution yet. You have some errors and it's incorrect. Okay, you have to make left and right side be equal once you introduce this total solution back into the equations of motion as in number 1. The second is I have to satisfy the initial conditions. And my initial condition contain here like this. First, the displacement at time 0 is 0. And the third conditions you have to check is when I perform the derivative with respect to time t, I will obtain the velocity, right? From x of time t be the x dot. That is the velocity. And introduce time t equal to 0. And check whether your solution provides the quantity of 0 or not. 0 velocity at time t equal to 0 or not. And if you can satisfy the 3 of this, you have to feel very confident that this is the solution. This is the exact solution. This is the correct solution. No one doubt on you. Okay. Please try to take a look at this example, recheck everything, and confirm everything yourself. Okay, I want you to learn how to prove or to get the correct solution yourself. No need for someone else to tell you it's good or bad, is correct or not correct. You don't need to ask anyone. You can ask yourself. Okay, and prove by yourself. It's simple like this. So let's do the same thing with the question number B and number C. Okay, and thanks Midlin a lot about this question, and let everyone try to recheck the example, this example. Okay, so if you don't have more questions on this, I think it's a time to show you some, before I go further about the resonance. It's better to see something from the video clip. Okay, I have some question on the TOA painting, right? The colors. Okay, maybe let explain and discuss with you again later. But before, I would like you to see some small clip on the test of the single degree freedom system to show you the resonance phenomenon. Maybe here. Okay, let's do it. Okay, this is just a check table. Before I get into the story, let me a little bit introduce you some information before. This is a small experiment done by Professor Kwong, and he do something like this. He put the single degree freedom system on a check table. A clean color is the check table connected with the linear motor, and that it can drive this system of the table to move left and right in a sinusoidal form, very close to a sine function. And then on the top of the table, you see there are three systems which can be treated or considered as a single degree freedoms. The first system is a kind of a back lapper, right? Is to represent the mass and to help us to have a clear visualization, so you can see it clearly. You put the back big thick lapper on the top, and that has the same mass with the three system. You see, it's the same amount of the thick lapper pad they put on the frames, and that frame is the portal frame. It's a kind of thing, I think is a kind of steel, very thin steel, how do you say, lip bond or steel plate, but it's very thin. To be have like two columns of the building. And that will a part that produce the stiffness to the system, right? So you have the mass. Every system, the three system from left to right, if I put the number for you, maybe it's the number, let I call you ABC, maybe it's better. I'm sorry, eraser, and then I do it again. And it could be something like this one is A, let me call it B, and that one is C. There's the same mass, but the stiffness of the system, the three systems are different. For sure, if the columns are the steel plate, the thin plate that made from steel have the same side, I mean the same width, you can imagine that the building C, they have a longer columns, right? And therefore the stiffness of the column like this will be depending on the length of the column itself. 1 over length power, maybe power 3. What does it mean? It means that the stiffness of the building C has smaller stiffness than the building B. And the stiffness of the building B has smaller stiffness than the building A. So in terms of the frequency, we often refer to the equation saying that the omega equal to square root of K over M. Okay, we often say that omega equal to square root of K over M. And since the system has the same mass, therefore we can expect that the frequency of a building A, frequency of the building A is higher than the frequency of the building B and the frequency of the building C, like that. Okay. So in this test, you will see that they will keep the check table move left and right at a very, very small amount of movement. I don't know how large it is. Maybe it's just movement of 1 centimeter at the support. And they change the frequency from slow to very high speed. They make it faster and faster. They keep The excitation could be something like a function like this, the excitation at the cow. So function of the psi big omega t. Okay, and they change the big omega t increasing and increasing from 0 to amount that higher and higher. What we expect to have, you will see in this video script, that we get a resonance. They will get the resonance. The first, we expect that the building C will get the resonance first. And after you increase the omega, the big omega, a little bit more, the building B, number B, will get into the resonance vibrations. And once they increase more and more frequency of the shaking of the ground, of the support of the table, lastly, I think building number A will be in the resonance. We will see this phenomenon together. Let's see it. Let me move, stop here, there, and let put the, see the ground motion, they fix the amplitude. So the magnitude of the movement is kept the same. They don't change the amplitude, but they change only the frequency of the table to be, it's very slow, right? Okay, it's same. Building number C, I think. We'll go into the resonance first. And you see the movement of building C. We check. See, when the building C go too close to resonance, the vibration is very large. At the same time, building A and building B feel nothing. That is occur at the 4 hertz, they said. You see how large it is. The cloud move only maybe a half centimeter, but the movement of the building C, I think is maybe 5 centimeters. However, when they increase the frequency more and more, the amplitude of building C reduced to smaller. Why the movement of building B is look terrible now. This means with this high frequency, building B go to resonance again at 6.35 hertz, they said. But they kept increasing the shaking frequency, and it found to be that the vibration of building B becomes smaller and smaller. And the last one, at a very, very high frequency of the excitation of the cloud, we can expect building A will go into resonance phenomenon. Let's see. It's not go to the resonance yet. It's close to. This is close to the end of the clip. Okay. At 11.35, they said this is a resonance of the building A. And it stopped very fast. Okay, it's like that. Well, I try to explain to all of you is, let me remove the, clear all the drawings. Okay. It's about the resonance. Let's come back to the equations that we found after we have seen the video clip like that. It's no doubt is try to prove the mathematics we obtained before about the DF. This one, equation number 33. Why the DF is defined as the dynamic amplification factor. The difference we seen in the clip and this chapter is, in this chapter, we introduce the force directly to the mass. In this chapter, the DF we define like this. The mass M subject to the force. I'm sorry. Okay. The external force is directly applied to the mass. Or in the building model, you can imagine that the force is acting like this. But the video clip, we have seen the thing is a little bit different. The force is not directly applied to the mass, but the ground or the support is moved with time, shaking like the earthquake. And this will be discussed again in chapter, I think this is 4, 5, 6, I think, about the ground motions. But believe me, the behavior is rather the same, very similar. There's some difference, but at the resonance, they share close to each other. I mean, it's pretty similar phenomena about the resonance. Therefore, this is let it confirm the mathematics we obtain that if the frequency of the excitations close to the natural frequency of the building itself, the ratio beta close to 1, then you get the resonance of your building. And once you get the resonance of your building, you see, you can expect a very, very high amplitude of the vibrations, depending on how much the damping ratio you have. This amplitude at the resonance, the amount of the amplitude, percent. If you introduce percent equal to 0.05, you will obtain the number 10 like this, right? And you obtain the amplitude of the resonance gonna be 10. Very large, comparing with the static deformation or movement. The phenomenon of the resonance is very, very interesting. But before you or we get into the discussion of this phenomenon in detail, a little bit more in detail, I would like to look at this frequency spectrum. But now, let you consider the frequency ratio close to zero first. This is A. At the state A, the frequency ratio is zero. When it's zero, what does it mean? It means that your frequency omega close to zero. When the omega close to zero, please don't be confused about this one. Many of us will feel something like this. I think the x of time t is a function of the, oh, maybe you're not confused of the, let me explain this way. If the frequency big omega, not zero, but close to zero. For example, big omega equal to 0.00001. It looks like I apply the force F. This is a time t, this is a force function. I apply the force F like this. Very, very slow. It will take maybe 1 year to go up and down. So in the time period of maybe 1 hour or 2 hours, maybe this is a 1 hour, in the unit a second, you will feel very small change in the force function because the period is very, very long. The frequency is very, very small. If we take 1 day or 1 year to go from +1 to -1 in the term of psi function. Therefore, within 1 hour, remember our building, subject to the earthquake, subject to the wind loading, or any other type of the excitations, it's just 1 minute, 2 minutes, or maybe just 10 minutes or 1 hour at most for the typhoon or the storm, for example. Earthquake, you are thinking about just maybe 10 seconds, 10 seconds or a half minute, 30 seconds, and then it's gone. So when I say that the force function is largely constant for 1 hour, this is already static relative to the frequency of the building, civil engineering buildings. It looks like the world of static already. Therefore, if your frequency is very, very small, in this case, case A, you can expect the static deformations. When this is static information, it means the deformation is explained by F equal to Kx. And your X here, maybe X there, is F0 over K. That's why the dF is exactly 1. This is static case. In other words, it's static. Once I increase the frequency a little bit, you see the DAF become something like increasing with the frequency that I increased. And once you go to the case B, where the omega, the big omega, equal to small omega. This is the resonance. And the amplitude of the vibration increasing to 10 times for this 5% damping ratio system. We will go back to explain you why. The question, the big question is, why is so large like this? How come? Why the system has very large vibration? When the force is kept constant, F0 is never increased. I still apply the same amount of force to your building, F0. What I change is only the frequency. How your building movement is increased to 10 times to the static displacement that used to be before when I put this amount of force to your building when the frequency is 0. Why is so large like that? We will go back and explain and discuss with you again, but let me increase the frequency to 1.5 or 2 or 3. You will see something that when it's 1 point, actually it's not 1.5. Here is when it go to 1, is when the frequency ratio equal to square root 2. When the frequency ratio equal to square root 2, 1.4 something, right? It found that the DF has become 1.0 here. Oh, I'm sorry, it's not this case, this is a ground motion case. So let me remove this one. They're not the common point like that. Forget about the square root 2. This is the case of the ground motions. This is a force that acting on the mass, so they don't have a common point like that. But this one, you look at the curve, close to 1.5, you go to the DF equal to 1 again. And the interesting thing is often when C, big omega over small omega, let me do this, is greater than small omega 4 times, 10 times, 5 times, or 2 times for sure. The DAF become a number less than 1. Less than 1. It implies that the movement of your building is smaller. The dynamic movement is smaller than the static movement, which very good, right? So the stresses, the shear force, the moment in the beams in the columns of my building is very, very small in this case under the dynamic loading like this. Okay, so this is a T portion of the phenomena or the characteristic of the system under the harmonic force. The very interesting thing is the case B, where the resonances occur. Why the building motion or movement is very large. And to explain this, even though the DF shows very clear that at the resonance, if we go very large from the DF, if I introduce beta equal to 1, this term goes to 0. When it goes to 0, as the denominator, right, is the 1 over this number. This number, I think mathematically we call it a denominator, maybe. When the denominator is very small, you will get a very large DF. And this term, 2 per psi beta. Remember, for civil engineering applications, our building precise, very, very small too. It's 0.05, 0.02, 0.01. And once you take the square and take the square root, is all the same, right? So during the resonance, you obtain something like this, right? 2 precise. Because beta is equal to 1 in this case. And that's why you go to 10. If your precise is 0.05, you get 10 times. 10 for the DF. Okay, so let me remove this one, otherwise confused. And the resonance is like that. Mathematically, it's explained by this equation number 33. But the question is about what is the physical meaning? Why the system like this is when it's go to resonance, the amplitude is very large. I would like to explain this phenomenon through it's better to understand through the energy concept. When I say the energy concept, I would like to consider something like this. Remember, is the force function here is a psi function. We assume that the force Ft is F0 psi big omega t. And the response we obtain, the x times t, if I look at only the particular solution. Okay. Xp psi big omega t minus Vp. The thing is happened is because the resonance, I said, it happens because the force that acting on my system try to inject the power, the energy to the structure. And during the resonance, it's happened the same phenomenon, like you play a swing. Do you know the swing? When we have, let me show you this one. Oh, I have a quiz on you about this problem. Remember, if I pair the input, the swing kit, let me Google for you. When you go to the playground, right? Kids play swing. Yeah, I found this. Let me share you this one. Okay. Children's kids, they play the swing. Even though we input the force to the swing system with a very small amount of force, everybody can imagine that the kids don't have much force. They just try to put their body, right, with some small muscle and try to move, to drive the swing to be higher and higher and higher. And if you ask, for example, this kid, this young lady, to push some people to go to maybe 90 degree or 180 degree for the swing, it's very hard for her because they don't have so much force. But they can play the swing. Go to 90 degree. It's easy for them if they want to play and they want to learn too. not so difficult. The same thing with the resonance. She tried to input the energy to the swing system. And the problem is, to do so, I need some time. I need some time to inject more and more energy into the system. I cannot do in just one cycle or one round or playing the swing. I need maybe 10 cycles to move my body from 0 degree to 90 degree when playing the swing. You can imagine, right? You swing, first cycle, second cycle is higher and higher and higher and higher. It looks like we try to inject the energy to the system more and more and more and more. And this happens to the resonance system as well. We know that the work done equal to the integration of the external force and the X, something like this, right? And if you change the integrand from the X to time T, you got something like this. And this is the power that you have to, it's a dot product of the force with the velocity, dt. And to inject the work or energy into the system as much as possible. In this case, I think the x dot p need to be a function like this. I'm sorry. It should be something like a x dot p and the psi function. I need this at resonance. You need to be the same phase. If the force is psi function, the velocity of my building or my structure at the resonance, I'm pretty sure is the same psi function, the same phase of the psi function. They don't have the minus or plus Vp anymore. Become 0. This is because we make this term to be the term that's always positive. Remember the sine and cosine, you have plus, minus, and change with time. But if you say this is a function of the sine square, the thing is different. The term will be always positive. And this will happen only when the force and the velocity x dot is they're both the same function, sine or cosine. If the force I assume sine, the velocity will be sine, the same function with the same phase. No phi p anymore. Only pure sine function with the same function as a force. To make the product of them, f dot x force multiplied with the velocity become a sine square. And this guarantee that every time instant but if the x dot is not a sine function, it's a cosine function. When the force is sine function, if the x dot is a cosine function, or when the x dot is a sine function plus or minus phi p with some phase difference, we're pretty sure that that is not the resonance anymore, since the energy will not effectively inject to the system, into the system. Some portion of time, the energy will input to the system, but some other portion of time, period of time, maybe your energy will be extracted out from the system. So we cannot expect that the vibration will be very large, because you don't always input the energy into the system, as in the case of sine square. So the sine square is the case of resonance. It's a case of at every time instant, you try to input from the external force, you try to inject the energy into the system, always positive like this. So if you let the time go, there will be larger and larger energy in your system. At this point, one of you might have a question. Oh, if the explanation is like this, it doesn't mean, does it mean like my system will go to infinity? The displacement will go to infinity? The question is, the answer is no. The system will not go to infinity. Why? The question is why? Because you input the energy into my system, always positive like this. The total energy in my system is increase. And if I let the time go into infinity, the total energy of my building or my system could be infinity too. But in fact, it's not. The reason is you have the damping. In your system, you have the term Cx dot. That is the damping. Remember that my equation is mx double dot plus Cx dot plus Kx equal to Ft. I have the damping. If you inject the energy to me so much, my vibration is go larger and larger. But because I have the damping term here will try to remove the energy or extract the energy from the building. And if this term is larger, mean the x dot is very large, there will be the equilibrium of the energy as well, where the additional input of the energy, if you want to input the energy from the cycle number 11, for example, at the first cycle, the damping is not work so well because the vibration is still small. X dot is small. So you can inject the energy to the system, okay? The second cycle, you can inject the energy to the system. The third cycle, you can inject the energy to the system. The third, the fifth, the sixth, the 7, 8, 9, 10, assume 10 cycle, you can inject more and more energy to the system. But after 10, I assume allow 10, because the curve is like this. If you look at the resonance curve, go like this. And this one is not 10. Maybe just 4 cycle and 5 cycle is already steady state motion. You see? So you take maybe 5 cycle to go from 0 to the steady state. And at the steady state, you cannot increase the amplitude anymore, even though it's resonance, because the damping term. Because the damping will be increase the capacity to extract the energy or remove the energy from your system. And the rate of the extraction or the rate of remove of energy is the same with the rate of inject the energy into the system. That's why they go steady state. No more, no, like the amplitude is steady, constant. It's not increased anymore after the steady state of the resonance phenomenon. Okay? This thing will prove or show you if I remove this term. If I remove the damping, what happened? I will show you from the mathematics of equation number 33. See, if let's look at 33 at resonance beta equal to 1. This equal to 1 for sure. This equal to 1. But let the damping ratio is 0. You can see the number, right? It seems like this, infinity. If you don't have the damping, I agree with you. At the resonance, you input more and more energy into the system. So the vibration of the building become larger and larger and go to infinity at maybe 10 hours after. The building collapse, we can expect something like that. If the damping is 0, theoretically speaking, the building movement will approach infinity, because you don't have any term to help your system or your building to extract the energy or remove the energy from them. Okay, hope you understand this. Because the term of the mx double dot and kx is what they call is the conservative term. Is the term that you can change the energy from kinetics to potential energy, right? So energy is not removed from the system from the mass term and the stiffness term. The only term that can remove the energy is the damping. That's why we need the damping. Otherwise, at the resonance, your system will go to infinity. This is what I try to explain to you. And now we have a problem to ask you. And this is about the quiz that I try to ask you. Okay, let's thinking about the swing problem. And I would like you to select, let me try to, which one is good. I try to find the photo that is easy to, I don't want to draw the, but you can imagine, it's quite easy to draw now, it's a wing. Okay, about the quiz. Let you assume you were a kid sitting on the seat of the swing. Not good at drawing a thing. Okay, put the leg like this. Okay, want to play the swing? Of course, the swing, this is a zero position, okay? You want to let it move back and forth like this. And if I said that you, as the man or the girl who plays swing problem, at a time, very small time instant, you can input the force like this. This is a time. This is, oh, I'm sorry. This is a force function that I can play the swing. This is a very small time, maybe only 1 second. The width of this is just 1 second. It's a kind of impact force, right? The amplitude is F0. So F0 is this direction is positive. Positive is here, right? You can put the force like this, F0, and then you stop. When I play the swing, I will push on your back and you start to go from 0 to maybe A position. Let me start like this. At 0 is the A position. I start with some initial displacement for you. Maybe I push you here. And let you go. Okay. I pull you to this position, the pink position, and release you. So you go to 0 position, you go to the positive position. Okay. Like you go to A position, you go to B position there, and you go back to C position, and you go to D position. Can you imagine this? Go to B position, and then you go back. It's very hard for me to explain this, sorry. And then you go back to the C position, and then you go to this position, the maximum negative displacement, D position. Okay, from the, I start from time 0 here, and you swing to A position, B position, go back to C position, and go to the maximum negative displacement D position. And I hope if you imagine more, if we go to E position. Again, my question is very simple. If I have the ability to exert the force F0 to the system in the positive direction like this. This is a positive direction, right? Let's define the positive direction is from left to right. When you better apply the force, whether at A position, or you waiting until the swing go to the B position and you apply the force F0, or you waiting until the swing go back to the C position, or even you waiting until the swing go deep backward until the B position. You have 4 choices. Which position you will apply the force F0? Remember the F0 you can apply is only 1 second, very small 1 second only, like the impact force that you can move from left to right. What I try to ask you is to select which position is the best to apply the force. If the force is defined like the impact force like this, and the direction is from left to right, and the objective is to increase the swing amplitude. I want to make my swing to be larger, higher. Okay, this is the objective. So I will put on the Padlet and ask you to select when is the best to apply the force to increase the swing amplitude. Understand? Anybody has a question on this quiz? No, if you don't say anything, let me share you with the Padlet. You have 5 minutes to thinking about this.
Recording in progress.
Okay, I think I already. I'm sorry. I already sent you the chat. I'm sorry, in the chat. So I think I sent you already the Padlet link on the chat. Okay. Don't forget to input your ID. One of you just say the answer, but don't provide the student ID. Please provide me also your student ID. Okay, good. Okay, 1 minute more. This one is actually some very small calculation if you want to check the answer is good or bad, but it not take so long time, very easy. But believe me, you have different feeling. I got from you, I have already A, B, C, D, 4 of them. Okay, 1 minute more. And we will discuss about this and the color mixing machine as well. Okay, I obtained 16 of the answer from you. Oh, I see one try to connect again. 17, it should be okay, right? Since we have only 18 people in the Zoom. Okay, good. Okay, the time's up. I will disconnect the Padlet. Okay, good. Let me conclude the solution, the answer from all of you. Okay, so B, A, D, 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 B, D, D, B, D, B, A, D, C, D, A, D. You see, many of you say D. Some put B, C, and A, and A. The answer, the correct answer is you have to do like this. You better ask yourself which position that you can make or input large energy into the system, the largest energy into the system. To answer this, I also need the integration that I shown you before, the work done that can be calculated from the integration of force F multiplied with the velocity x dot dt. Remember, your time to input the energy is only 1 second, since the force here is 1 second. You have the time window of the integration only 1 second. And I will try to use or to make use this 1 second to be the most effective way of input the energy to the system, to the swing system. To do so, you know what I want is the x dot. I have to find the x dot. What's the x dot when I go to the A position? And what the x dot when I go to the B position? And what the x dot when I go to C position and D position? Let me write down for you a bit about this. At the A position, I think at A position, the x dot, maybe I put it in the table form, A, B, C, and D. And this is my x dot, okay? At A position, maybe I say is maximum, positive maximum. When go to B position, I think the x dot is 0. When the swing go back to C position, I think is the negative. The velocity is on the negative direction, is the minus max. And when the swing go to the D position, again is 0. Because the velocity there is 0. My answer now become very clear. If I want to increase the swing to the larger or higher position or higher amplitude, I will apply the external force F at A position. At A position, because the force is positive, maximum positive, the force is here, right? It's F0. And the x dot is positive maximum. Therefore, the integrations of these two terms, if we compute the work here, it be the maximum work done by the force. You cannot find any other position better than this. For example, if you apply the force at B position, you got 0 work done. You apply the force for nothing here. If you apply the force at the D position, D dot, the same thing. The feeling from the mathematics say 0 work done. And if you apply the force at C position, this is the worst case. You try to stop the swing. You try to extract because the work done become negative number. It's implied that you try to stop. You try to make the energy, the swing energy smaller. Instead of input energy, you get some output from them. You try to remove the energy from the system. If you select the C cat, you try to stop the swing. Okay? Any questions on the quiz? My answer is A position. And it seems 1, 2, 3, only 3 of you get the score from today's quiz. Only 3 of you. Remember the swing everybody can play, even kids. All of you can play the swing, I'm sure. But we never feeling when we apply the force. We just naturally play it. And it seems everybody can do this swing problem without any difficulty and without any study on the dynamics or physics. But today, if I ask you, which feeling when you apply the force? Maybe it's quite it easy question, but it's quite hard to answer, right? And it seems only 3 of you can say A to me. A position, 3 of you. Any questions? If you don't have the questions on this, please me discuss about the TOA painting again. I left this question on you last week, I think. Any idea so far? Can you try to minimize the vibration or to stop the vibrations during the operations of the color mixing in their manufacturers, and put the mortar and the mixing pad? I don't know how to call it. Any idea from you?
I have, but I think it's very stress. Can I tell you?
Sure. I'm happy to listen, please.
I think if we change a directions of motor, for example, on the top of this frame, machines 1. Is machine 1 is the direction of machine 1 is clockwise. And for that, the machine 2, we need to change the directions of mixture number 2 to anti-clockwise. And I think the total force F1 and F2 will be 0. But I'm not sure.
Very good. Yeah.
You understand me?
You say not sure, but it's very good. If I understand you correctly, you try to change the directions of the mortar. You said something about the keywords is about clockwise and counterclockwise on the first machine and the second machine and the third machine. That's very good and very smart idea. I also share the same opinion like you to the manager of this manufacturer. Just change the face. Go clockwise. Yeah, go clockwise and counterclockwise and put the initial position of the pad, I mean the mixing machine, to be 90 degree or 180 degree, for example, when you start the machine. That totally remove the vibration. Totally. Very good. Very, very smart idea. Very good. And thanks for sharing to us.
Thank you.
It's like, this is very good as your friends sharing with us. Just change the way that the motor, we cannot change the frequency, but we can change the direction. The direction of the machine maybe a little bit effect on they want to, how to say, they change the angle of the mixing pedal as well, but it's quite easy for them to adjust. When I say I want to go counterclockwise, I want to go clockwise, they say, oh, okay, it's possible. They can adjust the mixing for us. Therefore, the total force, as your friends explained before, is minimized. We will cancel each other. The force, the mixing force, will cancel each other from the mixing machine number 1 on the top floor and number 2 on the second floor. And that's why the vibration of the steel frame is very small after the programs or control the mixing like that. Okay, thank you for sharing. That is good, and I agree with you. Who answered me is very good. Any other questions so far about the harmonic force vibrations? Okay, let me do this way. I think it's not so hard for you to understand the next chapter. Is chapter number 5, right? Number 5 is about the harmonic periodic force vibration. So I will, on this coming Thursday, I will come to a very short brief on this, and maybe I will provide you also the previous class on the periodic force vibration, last year lectures, to share you with the video link so that you can maybe have a look on this coming Thursday. But let me do this way. I will ask you this coming Thursday to have a look my previous video that explained about the chapter 5. And next week, Tuesday, I will come and try to discuss with you about this, because I don't want to go into the details so much about the handout. It's quite straightforward and it's quite easy for you to learn and study yourself. I need from you is about the discussion. I need from you is about the questions, okay, about this chapter. And I will try to use chapter 5 this way. So this coming Thursday, I will provide you the video link of the previous explanation or discussion, maybe last year, so that you can self-study. Please take a look and watch that one and try to understand the chapter yourself. And next week on Tuesday, we will come to discuss about the chapter 5 again together. Since we have only 3 weeks left before the midterm, I do believe that I can finish in time. It's not so difficult for me to complete the lecture, chapter 6 and chapter 7. Therefore, we have 3 weeks, and I would like to push for discussion, most of them. I prefer to discuss with you on chapter 5, chapter 6, and chapter 7. So on chapter 5, after you self-study, I will try to find one example or one more example, maybe more practical example, so that you can try to make your knowledge, utilize your knowledge of chapter 5 to solve the real problems together with me, with your friends, and we will discuss on the problems. It will be a problem-based, likely is like that. Okay, I will provide the information to the live group if you don't have any questions so far. Okay, thank you so much for today, and hope to see you next week on Tuesday. Okay, have a good day and goodbye.
Thank you. Goodbye.
Thank you. Welcome. Bye bye.